Topic for this morning. It's intro to edge computing, and basically we'll be discussing what's it all about, and how does it relate to cloud. So our short agenda would be key components, edge computing's current challenges and limitations, its similarities with cloud, no, and of course differences. So we could determine where would edge computing and where would cloud computing be appropriate. And for starters, it's not really different. It's you would use edge computing most likely in combination with cloud. So it's good to know what kind of use cases they would be more appropriate into. Okay? Then lastly, we have a summary of key learning points. So what is edge computing? Hopefully, a lot of you were here no, last weekend when we discussed the cloud, no? And this is yung spin-off no, on what is edge computing. So this is a distributed computing paradigm no, where we would want to make processing no, and storage of data instantaneous. And for the most part now, we're bringing a lot of computing capability no, and storage capability as close to the device or the data source no, as possible. No? And advantage, of course, is we would have better control of data. And depends on how you look at it, it would reduce cost, no? And we would have faster insights no, and actions no, to basically enable no, streamlined operations and increase efficiency. So we would try to identify where we would be using this and how do we actually realize no, itong advantages na to. Okay, so for edge computing, no, we had this basic diagram on where it actually resides no, from Spiceworks, where you have your cloud and data center on top. No? So it's still gonna still be used. No? But what you can see here are edge devices or IoT, no? At the bottom, like cameras, telemetry, autonomous vehicles, robotics, even telecom. Okay? They are producing this data because they have sensors, they are generating data. And typically you would send all of this information to the cloud. No? That's what we had before. No? But we did realize that there has been some issues. For the most part, it works, no? But there are some use cases, very good use cases, that it would be a bit more unoptimized. No? If you send, let's say, if you have a camera system that maybe 10,000 cameras no? For a compound or a multi-campus deployment, no? Imagine all those 10,000 cameras would be shifting their data to the data center or to the cloud. There are implications that needs to be made, like bandwidth, latency, and the amount of information that now has to be stored and processed in the cloud. That's also going to be an issue. So we'll see them in a bit. No? And what we determined was, well, if we cannot or it's not optimal for us to send everything to the cloud and have the processing there, why not do some processing on the device itself, no? And maybe have some intermediary platform, no? To connect them and run, no? Dun sa before no? Sending them to the cloud, no? Okay. So short of history. These are actually edge computing is actually based on content distribution networks. No? It was developed in the 1990s. Basically to serve videos, pictures, no, when bandwidth was very smaller, very scarce bandwidth in the 1990s. Not sure if a lot of you were online then. Maybe most of you haven't been born yet in the 90s, no? Where there are dial-up modems, no? And it could, I think I remember some modems are running at 14.4 kilobits per second, and that's the turbo version. And I've seen campuses no run on, they have good maybe 10 Mbps network infrastructure in the campus, and then you have your upstream would be 14.4, even lower no the time. And of course, to a degree, no, the content like YouTube and Flickr, no, and Instagram, no, it's not, they weren't created then yet. No? So a lot of the content were text. No? So these were a small bandwidth is still usable. No, we didn't even have much of a chat program back then. It's just I would say maybe IRC would be our equivalent of messengers or Telegram or Viber. So that's it. So text-based computer networks were in, no, in the 90s, but slowly, when browser was modern web browsers were starting to evolve. Content like pictures, initially it's pictures, no, and then eventually encoding videos, no, like MPEGs and the likes, no, started needing the increase, no, for bandwidth. Um, Hence, this content provider, no, we're trying to figure out now that okay, even them, they had problems with hosting, no, because well, I think if you have a 10 Mbps back then, which would be very expensive, no, all of these computers, no, that's starting to popping up, and endpoints, no, and harvesting your content, your 10 Mbps would be maxed out easily. So, they started designing this. But what if we could have this content, no, being close enough to our consumers, no? Hence, in the 2000s, no, they evolved these issues, no, to CDNs, no, and started hosting this content, no. Initially, it was just static content, no, on the edge servers near, no, the consumers. No? And how does CDN works? No? So this is an example from Hostinger where you have your users and they would be connecting to the edge servers for the content. So maybe we could use an example here like Netflix. No? So let's say Netflix would have a new movie that they're gonna be releasing, no? And of course they're gonna upload it to their main server. And then for this main server, they would have some predictive capability, no, on which market, no, on which geographical region would this new movie would be more, how you call this, more users, no, would want to watch this movie. No? But for the most part, especially if it's a newly released movies, especially during the pandemic when most people doesn't have anything better to do, no? It will be consumed immediately. So from the origin server, it's gonna be replicated to the edge server, which is typically a box on a data center near your consumers. No? So like here in the Philippines, no, we have Netflix boxes that Netflix coordinates, no, with our internet exchange. So we have one Netflix server in OpenIX. Our telcos, no, let's say PLDT, Globe, Converge, no, they would want an edge servers within their infrastructure. Why? So that when consumers, no, ask for a movie, it will not have to go through their infrastructure and then go out, no, to the submarine cable and then eventually reach the Netflix main server in the US, let's say, like that. So because if you have, let's say, if you're a telco like Globe, Smart, or Converge, no, that would have a lot of consumers attempting to watch a movie, that would saturate your infrastructure, your outbound infrastructure. Um, so if they have the edge servers within their infrastructure, what the consumer's app would do is, okay, Netflix, go to, let's say, AWS login server of Netflix now that hosts their catalog. No? And they click on a movie there. What the Netflix would know is that, okay, your IP is from the Philippines and you are actually from Globe. Okay, this link of the movie you want to watch is actually located here. No? They're gonna provide you with a unique URL that would actually direct you to a server, no, in Globe Telecoms. No? And once you click that movie, your content would be served, no, from your ISP. And that would mean you would be consuming your bandwidth, at least your subscription to the ISP. No? But the ISP would have a lesser consumption of the outbound and inbound, no, from the external point, no, of their infrastructure, a bit less, no, because now they only have to download that movie once on their edge server, and they could serve thousands of people, no, on consumers, even hundreds of thousands of consumers. And imagine those bandwidth savings, no, from the ISP's point of view, that those thousands or hundred thousands of consumers will now not need, no, to consume their external bandwidth. So that's going to be a huge saving. So that is basically a short of how CDN works, and that is technically how Edge, why Edge computing came into play, no? Where they wanted to optimize, no, this content delivery. Okay, and maybe a short graphic history on edge computing is, remember, this is in the maybe mid 2000s, not to 2010s, now where we have done maybe 2 decades of personal computing since the 90s, no? And then we started seeing this virtualization coming being mainstream, no? And note, virtualization has been there since the 70s, no? It's used in mainframes, no? But now it's commoditized, no? And people started saying that okay, well, they realized, no, that their internal servers would have some issues with accessibility, no, of users, no, where you could only access it if you are in the infrastructure. Well, some of it were solved, no, via VPN. You could VPN into your infrastructure and then you could access your internal server. But the cloud advocates are saying that, well, that would still entail that you need to maintain your own infrastructure, which they're trying to move, no? Some of the responsibility to the cloud providers, as you've seen in my talk last week, no, where there is a shared responsibility model. So a lot of users and cloud advocates wants you, no, to not maintain power, cooling, storage, and bandwidth, no, shift it just to the cloud, and hence the first box, no, where they were saying that you don't need this server anymore. You just connect to the cloud. Okay. But as you seen in the previous slide, where on the CDNs now, where they started realizing now that okay, we migrated everything to the cloud, but now the, our bandwidth is not able to handle it, so we need to increase it. So basically, you have cost. And then even if you have bandwidth, you cannot beat physics. No, it's still gonna be limited with the speed of light. No, while it is very fast, the moment you cross borders, no, via submarine cable, your data crosses borders via submarine cable, there would be latency. Definitely, I'm not sure if anyone would be able to discover, no, a way to transfer data faster than the speed of light. I mean, of course, there's going to be those in the science fiction, no? But so far, if you've seen movies with accurate science fiction, they would have this latency in transmitting information, no, to terrestrial and maybe space travel, no. Example, this is if I remember correctly, no, if you want to transmit something to Mars or maybe the moon, I forgot which celestial body that would be, no, it would take 8 minutes, no, to send that information and back. No? So imagine your ping, no? You ping a packet, no, it's gonna get a response after 8 minutes. And well, with the cloud, it's a bit smaller, no? It's in the millisecond. No? But if you have devices, no, like say an autonomous vehicle, no, that needs to decide where it senses, no, an incoming pedestrian, no, that you're gonna hit. No, you don't want that latency to be a factor, no, for the decision. You got the sensor, so sometime later you want that processing to be near your users, no, or the data that's generating, or the device that needs those information. So they, I wouldn't say ironically, no, but while they are putting servers and compute nodes, no, near or on the devices itself, now it's not technically something, no, that would collate all data. It's to help this IoTs, these edge devices, no, for additional computation power so that they would be able to decide faster without the need to connect to and contact, no, servers in the cloud, which could have some issues with latency, maybe bandwidth, and maybe connectivity, no? So especially if you have a lot of devices that your data would pass through, no? Routers, switches, submarine cables, no? Eventually data centers. No? There's a lot of point of failures on that route, no? While we have made it very uh, as the network guys would say, hyper-converged, no, where any downtime would just be recalculated, no, the path would be recalculated in a few milliseconds, no. You don't want that kind of idea if it's a life and death environment, no, to decide, no, whether to shut down this valve, turn left, turn right. That would have to be decided within the device itself. Also. But this comic strip na somehow accurately captures, no, why we are in the edge computing era. So we have endpoints, no? We have smart endpoints this day and age, no? Where most of this would be sent, no, to a centralized platform. Typically, again, it's in an internal server or cloud based, either via LAN or WAN, maybe both. And this crunches the data and sends an output back to the endpoint. And as you've seen, I explained a while ago, na if you have a lot more devices, this is going to be a scalability issue. So the volume of data that's also going to be sent, it's also going to be an issue. And of course, latency too. So maybe got two quick examples here. No? So let's say you have smart camera system to the tune of 10,000 cameras, no? Internet connected cameras. No? So imagine the volume and bandwidth, no? That you're gonna be able to consume when all of those 10,000 cameras are sending their video stream, no, to the cloud. Well, it is possible you could do that, but tends to be now very expensive. And there would also be 10,000 feeds. No? Imagine the processing capability you need, no, on your cloud platform. Of course, you could expand, no, as much as your credit card could entail. No? But they would still, the more data you dump, no, the more compute power you need, no, centrally within the cloud. No? So aside from transmission latency, you're gonna have processing latency because they would have to process all these 10,000 streams. So let's say you have a person detection on the camera. No? The camera sees the person, but if it's a dumb camera, it would still have to send that data to the cloud, and the cloud would process it frame per frame, or maybe a sample. No? Especially if you are trying to conserve compute power, typically you'll try to analyze it maybe 10 frames per second or maybe 1 frame per second. No? You would tune that as needed. But I've seen high resolution and high speed camera, no, that was used for that was used for an area where there was something was stolen, no? But the camera did not detect the person, or the engine did not detect the person because the person was there in and out less than a second, no? And for example, they are processing it of 1 frame per second or maybe 1 frame per 2 to 3 seconds, no? Because of the amount of data that they had to process, and they have limited compute power. Those 2 to 3 second gap could have been the instance where the theft occurred, no? And the camera might have actually missed the person there, no? So there was no alert, no? By the time you look at it, why did the object went missing, no? And when you need a person to review, that becomes a bottleneck, no? And that's where they would see, no, that there was a person who swiped this item and then left, no? But the camera did not alert because they're processing frames, no? The interval to process those frames has been increased because they cannot do it close to real time as possible. They're processing frames, no? The interval to process those frames has been increased because they cannot do it close to real time as possible. So two things, no? They could request to increase their compute capacity, but that would now correlates to they would increase the cost. So they need to solve that kind of issue. Okay? So what are key components, no, in edge computing as with cloud? So we have data flows, no, from the edge devices, the IoTs, typically would send them to edge gateways, then edge data centers, and then the cloud. No? So cloud is still, of course, it's still a key component, no, in edge computing. We won't be able to take away the cloud anytime soon. Maybe it's gonna be there forever, but we'll see, no, where technology would lead us. No, but data now would need to be processed, no, and analyzed at various stages along this path, no? Depending on how we design this, what our specific requirements are, no? And use cases. No? So this one would, when deploying all these key components, it would help reduce, no, the issues now we've seen kanina, like latency, data privacy and security, and make it more efficient use, no, of network bandwidth, as we'll see later, no, when we discuss each and every point of this key components. So, well, we do have, of course, the edge devices. So these are devices that typically is collecting data or sensors, no? And they would process this data locally. So most of these devices would now have some sort of a compute power, no? And it could be anything, no? Smartphones, laptops, cameras, IoT devices, autonomous vehicles, no? They would have compute power. This modern equipment of such as this, no, would have compute power on their own. But typically, they are under utilized, no, the compute power back then was just to basically pick some items and program then what you're gonna do. No? But the processing side during the cloud era, no, they would have to send all of this data to a central location for processing. No? But now, with edge computing, no, they would want to utilize that, or they would want to upgrade the compute facilities of these devices, no, to be able to have a built-in processing capabilities. Or if they have some use case and programs that needs to be run, no, if the current one will not be sufficient, no, especially the compute power, no, they might need to upgrade the actual hardware for that. So, well, they could make basic decisions, no, on which data to quick analysis, which would require very little compute resource, no, and determine, no, if this data would be warranted to be uploaded, no, to the cloud. So that could be one of the use case for these edge devices as computing capabilities. And with the goal of helping reduce, no, the amount of data transmitted, no, and minimize latency. So let's go back to the use case of smart camera systems, no, with compute capabilities on the camera itself. It could be as simple as the difference, no, between a dumb IP camera that just sends all the data to the storage facility, maybe in the cloud or data center. No, then that would be a constant stream of maybe 5 Mbps per camera for an HD feed. No? But what if this a lot of these camera are actually monitoring area with no movements, no? Just for security, no? Let's say maybe 99% of the time it's just a static feed, no? If they don't have smart capabilities, they would be transmitting this static feed to a central location, again, data center or the cloud, with no value whatsoever. Just consuming bandwidth and resource. So what if that camera has some decision factor that, okay, I am seeing this, I saw this a few seconds ago, it's gonna be the same image, and I saw this 10 hours ago, it's still the same image kasi maybe it might be nighttime, no? And then suddenly the door opens. So they detected movement, they detected changes in the sensor from the previous static image. Then maybe it could now decide, no, okay, there were movements, there were changes in the lighting. It's not the same image as I was processing a few seconds ago. No, so they could now start. Well, hopefully they have storage, no, to also record that in case anything goes wrong. But now they could now trigger an alert that okay, there was some movement. Okay, and this data might need to be sent, no, to central location for validation. No? And on the central location, typically they would run that data to edge gateways and edge data centers. No? So we'll see in a bit. But that basically reduce the amount of data being transmitted. No? So from a constant stream of 5 Mbps to transmit data that's going to be the same, uh, they might be able to reduce that to that few second moment, no, where a door opened on the room and someone got some items, no, and well, might be legal or might be a theft, no, but they are able to record it, and now you'll need very small bandwidth to transmit it, no, and it's not going to be constant, no, so a lot of these 10,000 cameras would be able to fit their data to be transmitted on the limited bandwidth of the organization. And storing that event, no, would also be optimal, no, dun sa central location. And if you have people monitoring it, now imagine you have maybe 5 individuals monitoring 10,000 cameras. That's gonna be 2,000 cameras per individual. No? So that's I don't think that's gonna be a very efficient way to do it. But if you have an alert system that there's a movement or this is a critical part of, let's say, the organization or that area, no, and no one's supposed to be there in the first place, so you could have an alerting mechanism that would pop out dun sa console of the guy who would monitor it, and they would put and check that camera and have manual validation, no? Or it could be even validated with AI. No? Let's say there were movements, but there were no person that were detected, so that could be low priority. But if a person was detected and there was no person supposed to be there at that time, no, then they could start analyzing it and maybe call some guards to go and check out one of the area that had an alarm. So that's for edge devices. So I hope you could see now how no, compute resource, no, near or on the edge device itself starting to make sense. No. Again, rather than transmitting everything to a central location, you would have some sort of processing and decision-making capabilities, no, on the edge devices. Now we have edge data centers. So these are smaller scale data centers, no? Where of course it's not going to be on the edge devices itself, no, but it's close geographically, or not logically, something that you could work with, no? So you this basically entails, no, the the reduction of latency, improve bandwidth usage, and enhance data privacy, because now all this information did not be transmitted to the cloud, which would cross consume, no, your ISP's bandwidth, and eventually would entail more cost for them because well, diba, their cost from their data center to the consumers is lesser than, and it has more bandwidth, no, than their cost dun sa mga submarine cables, no, with internet connectivity. And then you could have this edge data centers, no, perform, no, powerful edge applications. So since it has more power, it has larger volumes, no, for data storage than edge gateways. No, you could have this, you could do the processing here. No, you could even if it's has good enough computing power with maybe some graphics card. No, you could have your maybe machine learning and AI decision making models, no, run on those data sets, no, before even sending it to the cloud. Again, this could be standalone facilities, could be integrated into existing infrastructure such as well, telecom towers, commercial buildings or industrial sites, or maybe ISPs. Again, we would just want to push, no, more compute power as close to the edge gateway as possible, and we want to optimize basically the process. No? So, but it's not just now collect the data and then submit to the cloud and process it there. So now you have to design your process to be more efficient, where collect data but filter it because you have limited compute power, let's say on the smart camera use case. No? Send this data to an edge gateways and then eventually edge data centers where they could start processing. No? Are you doing person detection, car plate recognition? No? And if you got those data, now you could send this now to the cloud where there would be someone monitoring it, no? Or push that data from the cloud back to a monitoring edge data center, and then you have your manual validation there. So that could also be a case. And of course, well, we have the cloud where these are most likely remote, no? Especially for Philippines, where most cloud providers or large scale cloud providers, no, don't have compute facilities here. Some of them would have connectivity facilities, no, where you could subscribe to a direct fiber connection to, let's say, AWS, no, via some local telcos, which is interesting, no? When you actually want to determine where these data centers are in, let's say, if you have AWS in Singapore, in Japan, or in Hong Kong, they're not actually disclosing, no, where these data centers are for security reasons. So that's it. But I mean, you'll have your fiber, no, in, let's say, a local data center that would connect directly to their facility in Singapore or Hong Kong or in Japan. No? It's interesting on how they would keep that big building data center location, no, as secretive as possible. And it's actually a common thing. No? If you have been to data centers, especially the big ones here, no, you will not see any markings on the building that would say that they are data centers. No? So I think it's part of their security because you'll have banking applications, government applications hosted on those servers that were co-located, and you don't want anyone to just know that, okay, the bank A is hosting their main servers here, then it might want to get in, no, to get some information. Of course, there's a lot of security considerations at play there, but it might cause disruptions. No? So they're not trying to identify themselves as data center anyway. Okay. But for the cloud, no, the cloud, no, while it is ingesting data from the edge infrastructure, what typically would be handled here are that are not time sensitive. These are pre-processed, filtered, or would require manual validation or more resource available than what's on the edge. So these are typically what kind of information that would be sent to the cloud. No? But with the amount of data that were already filtered from the edge devices to the gateways to the edge data center, up to the cloud. No? So you could, if you design it well, it's gonna be very efficient. No? That you are, especially if you're the one monitoring on the cloud. No? You are only receiving and processing data that were deemed not necessary to be uploaded. So typically when we see or help edge application design, there would be justification on why this certain type of data would need to be reaching the cloud. No? I mean, there needs to be a use case. All information needs to be accounted for because edge tends to be very expensive. Cloud tends to be very expensive. And of course, well, we also mentioned this a while ago, no, that the edge analytics and application needs to be coded and designed in a way that you have to make use, and you have, well, you decided to use edge computing at this point, no? You need to be able to use all these components, no, that you have spec'd out on why would you need a 1 GB memory and a 512 GB storage on, let's say, an edge device. So you would compute that. And when you do analyze, let's say, the edge device, okay, well, maybe 512 is a bit too much, especially if your gigabytes too much, if you're, let's say, discussing a 10,000 camera system. So if you could say na, okay, how much data do I need to be storing on the camera itself, no, for backup purposes, or maybe from regulatory compliance purposes, no? Maybe 512 would be too much, no? Maybe I could do it na maybe 128 gig would be enough, no? And that decision, no, to make it 25% of your original design, no, would actually be very prudent, no? That it would save a lot of money, no, for that kind of design. Na officially sorry, originally you wanted 512 gig, no, but upon analysis you only need 128, no. So you now have to just purchase 128 gig maybe SD card instead of 512, which would have great cost reduction, no? But that would mean that you really need to analyze that, no? Kasi the cost is gonna get doubled naman if, diba, you thought you're gonna use 128 gig without testing it, no? Only to find out you need something to the tune of 200 plus gigabyte. So you should have gotten 256 gig. You have to either change your policy that maybe we could only store half day, no? Not the one day now we were deeming, no? Because if we now want to comply, no, with the 1 day, the initial requirement to store 1 day, we will now have to purchase newer devices. But it's not unique to edge computing. No? It's just it becomes highlighted because you are now managing a lot of device, and if you make a wrong decision on the specs, no, of these items, no, edge gateways, edge devices, it would have a large impact on the cost. No? As with any project for that matter, any misspec would be catastrophic to the cost, no, and well, to your career too. So again, for this one, when you design edge analytics application, again, you want real time or near real time for faster decision making. No? So you need to spec out, no, what you actually need. You need to test those use case, and if these specs are not making sense, no, based on the application, you need either tone down the application's processing or upgrade, no, the specs that you need. No? It could be one or the other, no? Or you could have a sweet spot in between. As mentioned a while ago in the smart camera system, again, if you want the processing to be done on the device, no, maybe the device cannot do 60 frames per second processing. So you will need to tune the application to maybe just analyze and sample, no, maybe 1 frame per second, and then check if there's something that's you want to detect there and then trigger the alert. So you could tune the configuration based on the there and then trigger the alert. So you could tune the configuration based on the compute power you have. No? And then maybe as for the most part, no, you don't end up with a instantly 10,000 camera system. Typically, you start 1,000, then you start adding it. No? Then you could now start to tune. No? Maybe in 2 to 3 years time, the cost of those equipments drop. No, you could now afford to deploy the next batch with higher compute and higher storage. No, and then maybe you could have some tuning in your application that since this is the newer devices, no, we could now perform more this analytics more often than the previous generation. Okay. But you need to decide on that. You need to design your system, your edge analytics and application with those in mind, that you would be able to also mix and match this equipment and processing capability. So challenges and limitations. So we have this, we have a few challenge and limitation for cloud computing. So first, we have limited computing power and storage. Well, of course, edge devices will not have the processing capability as of now, no, of centralized data center, no, because you have computing power and storage limitations on these small devices. No, well, maybe in the future we could store a petabyte, no, on an SD card, which might be science fiction as of now, no? But there used to be a time maybe 10 years ago na we can't imagine 1 terabyte would fit, no, on one micro SD card. No, but it's now a possibility. So again, but for now, no, this edge, it's gonna be like that for quite some time. No? I don't think there's gonna be a time in the future where you'll have more compute and storage capacity on the edge devices than the data center. So I don't think it's gonna be the case. Well, I could be wrong, no? Maybe future generations 50 years from now would be laughing at this statement because it's gonna be not true anymore. But yeah, but for the most part, no, and physics would dictate too that edge devices would have less capabilities than data centers, centralized data centers. No? So that would mean the task that you are performing on these edge devices would be also limited, no? And your storage would also be slower, no? Especially for comparing SD card to NVMe and SSDs, no, in the data center and the server, the amount of write speed, no, and read speed on those devices in the SD card, in comparing with those fast storage, no, would be miles away, no. So you would also need to factor that in. So you need, basically it's a trade-off balancing between processing and storage capabilities, and you would need to design your edge application with that in mind. And of course, you would want to tweak certain variables, no, as uh, devices becomes or and specs now becomes upgraded, no, or maybe sometimes there are chances that specs would get downgraded. No? So I've seen that happen, no? For two reasons. No? One is cost, where this specific devices that we have spec'd out on the initial deployment, it turns out na upon running it for a few months na that lower capacity devices could also perform the job, no, with the graded processing, of course, but it's still within the bounds of our um our specifications, no, for that system, no? So that could also happen, but for the most part it's basically you're gonna encounter upgrading of specs. There's also security concerns, no? So in network security, we have what we call reduction of threat surface. And unfortunately, the more device you add to a network, no, you increase this attack surface, potential attack surface, no? And with edge devices, no, typically you would also deploy this out. Some of them would be deployed outside your premise, no? Like if you have smart sensor networks for weather, you're gonna deploy this in the mountains, no? And anyone would be able now to grab this device, no? And if you did not design or shows a device that's gonna be tamper resistant, no? If you have a knowledgeable threat actor, they would have access to these devices. And if they could JTAG or dump the configuration from those boards, no? Imagine the content of that configuration. No? You'll have the application there, the data that's stored there, connectivity to the wireless network. No? Even if it's encrypted, no? Let's say with WPA2, WPA3, well, the key has to be stored on the device for them to be able to communicate. So the attackers could extract the credentials and log into your network. Aside from just basic theft, no, where you would lose these devices. So this would be need to be factored in. Where do you place these devices, and is it within? Could we protect them physically? And we don't want to be adding edge devices only to be adding a potential attack surface on our infrastructure. So, and the thing is, it's harder to detect an attack from the inside, which these edge devices are, than those devices, those attacks coming from external sa network. No? So there are designs wherein you would actually consider these edge devices as an external devices from your infrastructure. So if you consider them an external data, which I would say that would be the best mindset, no? You would now need to filter any data that they are sending and validate them. And you basically do not, you basically somehow trust, but you validate and verify this information that these devices are sending to you, especially if it's not within your physical protection, if you deploy this outside your environment. And do note, you would want this to be designed, with breach in mind, wherein someone could have gotten that configuration and keys and encryption keys, on those devices. So what would you do to protect your infrastructure if you are assuming that these devices might be compromised? Again, someone might steal it, jump the config, and then log in with their own device and manipulate your telemetry, or maybe just infect the device itself. So typically, these IoTs are Linux boxes anyway. So they could flash their own firmware or load their own applications, no, to modify your telemetry. So you need to put that into again consideration. Infrastructure deployment cost. Maintaining an edge infrastructure, no, would be how you call this, a very complex, no, system, no, where sorry, you have devices. No, it's not like you deploy to the cloud and then now everyone would just need an app that you could easily deploy via the App Store and Play Store or a browser, no, to access these applications. Now you have actual devices that could be expensive and complex, where you need this you need to buy these items. If you need to be able to increase, no, your edge devices as needed, you would need to order them, and there would be latency on the delivery, no? Because it's not like cloud computing. It's not like cloud computing where you just click these boxes and you would be instantiated with a compute instance or whatever resource you need. No? Now you need to coordinate now with various organizations, and you need to make a purchase order before they pack it up and send it to you. And then once it arrives, now you need to configure it and then deploy it. So there would be some sort of project management and timing involved, with this, aside from the cost of procuring them, and deploying them. So uh, we need to factor that. Another is interoperability and standardization. So while edge computing, it has a wide range of devices, platforms, and protocol, it needs to be interoperable. While we would gun for a homogeneous deployment, no, with each and every device will be coming from a specific vendor, if you have designed and deployed, no, a lot of this electronic devices in the past, you know that you need to have a backup plan, no? For, let's say, for certain chips, while you prefer a specific vendor, no, there could be a time where that vendor is not able to provide you with that specific chip model that you need, no? So you might need to contact a different vendor which would have similar specs, no, again similar but not the same, no? And your devices should be able to handle it, or worse, no, that device itself is not really available. It's either end of life or someone just beat you to it. No? That they harvested all the processing capability of the plant. Not that they bought 2 years worth of device, no? And the plant cannot handle giving anyone else, no, those devices. No? So you'll have to go to different vendor and hoping that your system is capable enough, no, to be able to integrate and interoperate, no, with a different device, no, a model, no, or a different device vendor. So hence the necessity to use interoperable and standard protocols, no, would actually make a huge issue, no. If you design your own, no, and suddenly the device that the next device, no, you are trying to integrate will not be able to run those protocols and applications. So we need to put that also into consideration. For network connectivity, again, these devices, ideally, no, they rely on stable network connectivity. But yeah, if you're deploying, let's say, a sensor network in the fields or in the mountains, no, which could be affected by weather, your system needs to be designed to accommodate that. So let's say if you have a weather sensor and suddenly the connectivity was lost due to rain or some other instance, no? Maybe there was a tree, no, that obscures the line of sight, no, to an access point because of a flooding or a storm, no? um, Maybe the device could start, no, using its local storage to store this data. While you will not get that information immediately, the moment that the connectivity was restored, no, the device itself will now detect na, oh, okay, I'm now connected. So all this data that I was storing for the past 2 days where there was an obstruction with my line of sight, I could now send it back to the system. Na maybe that information might not, of course, it's not gonna be real time anymore, no? But maybe your analytics in the future, no, could still use that data, no? Since that device was able to still um, not lose this data. It was just not transmitted in real time. So again, connectivity would have to be considered greatly, no, for edge computing, especially those that are connecting via wireless. No? I've seen and have designed some sensor networks, no, where we would want their connectivity to be done via 3G back then. No? But we had issues because some of the location we want to deploy these networks, sensor networks, were they didn't have 3G on that area, or worse, no, they didn't have data connectivity. So we were able to design the system that, yeah, we prefer 3G, no, but in case it did not work, we could send our data via SMS, encoded SMS. We could actually fit a lot of information in 160 bytes, no? And that works. No? Device are designed to be dually connected, no, via data, so we just have a homogeneous device. And on areas where they are not able to connect to mobile data, they would send this information via SMS, a bit more sparse, no? Because those mobile data we could send the data in real time. This one we could program it to send the information that they collected for the past 15 minutes. So in an hour, we'll receive 4 of these messages and then interpolate it after the fact. So it's not real time, but their data is still important for predicting, no, environmental conditions. Okay. Then of course there's scalability issue where the more devices you put, no, this increase the load, no, on the network, on the edge gateways, on the data centers. No? So we need to manage this. The growth of infrastructure, well, we would only, of course, input and add devices, no, as needed on based on our requirements. No? And we just can't add data without thinking, no, where this data is gonna get stored, no, and processed. No? That means when you deploy semi-permanent components, no, like edge gateways and edge data centers, you would already have, no, some sort of a headroom when designing them. You cannot deploy it first time, no, with 100% capacity. That would mean even one device that you add would degrade the entire system. No? So you typically would have a headroom and maybe predict, no, what would be our volume in the next 2 to 3 years, where we would max out with still some headrooms, no? And then we could now start programming or asking, no, for an upgrade, no, of the system. As with any IT project for that matter, it's gonna be a challenge. No? There's also the issue with power consumption and management. Most of these devices would be running on battery operated compute nodes. No? So efficient power management is essential, no, for longevity of this device. And sometimes, no, you need to develop energy efficient hardware, no, where you have compute chip, no, but a lot of these features you might not need, no, or if you need a constant source of power, maybe you could have renewable energy sources like mini wind turbines or solar, no? But now what would happen if it has been raining for the past week, no? Where you lack uh, s- uh, solar energy, no? To power it up. So you typically would have battery still, no, as a backup. But the problem with battery is it's still limited. No? So again, if it's raining a week, your device might die, no, before the sun goes up again to power your and charge your equipment. But that would be part of the consideration. If you need these devices to be operating on all weather conditions, then you need to wire from the power grid. No, that's not uninterruptible, no, but lesser chance of going down, no, for this one. So you need to consider this. And with those that's running really on battery operation, we do compute, no, each and every feature that we would be asking those devices to perform, because some of this could consume a lot of power. So let's say if you are sensing something, let's say this smart camera system, from the sensor directly to the CPU and then analyze it if there's any other weird stuff going on that frame, no? That would be more efficient than from the sensor storing it to the SD card and then having your CPU get that data from the SD card, because it needs read and write still, no? And then process it and then send it, no? So you would need to be designing your applications in a much more energy efficient manner. So yeah, something to consider. And there is, lastly, no, maintenance and management for challenge limitation, where you have a device that is problematic, edge computing device that's problematic. Let's say, again, sensor network, and it's in the mountains for some reason. How would you design your maintenance management at that point? No? So, well, you could have all your tools, you could have all the spare parts, and then you could have someone hike up that location, no, and then troubleshoot it on site. Now, which would entail them opening up these devices, which might be dust sensitive or weather sensitive, and then figuring out what's wrong and then troubleshoot and replace that component there. Or maybe you have a device already, no? You bring it on site, you take out the faulty device, install a new one, and then bring down the device and for troubleshooting on the warehouse. No, you don't have to troubleshoot on site, and that's what I see. No, most organizations with sensors and edge computing devices are doing. No, they don't want to send all this equipment to troubleshoot, no, and open it up on site. They just replaced it, no, and then bring that faulty equipment sa warehouse for troubleshooting and repair. So, but that means you need to have a lot of these spare parts, a lot of these devices too, no, for replacement. You have to have headroom. No? Because if you have a faulty device and you actually are still gonna order additional edge device, then that's not gonna be up anytime soon. No? So yeah. So yeah, that's limitations and challenges for edge computing. Now we have similarities, no, for from cloud computing. So we got, they are used in combination for futuristic use case, no? It's like 5G and autonomous vehicles, no? Because the amount of bandwidth and reduced latency for 5G systems are making it possible, no, for these vehicles to be driven via machine learning, or even if you don't have machine learning, I've seen some use case where there is a remote driver. It's basically parang UAV, no, drones, no, but this time it's cars, no, that and someone could drive that car remotely. So it could be let's say a truck driver, no, that the truck driver would not to be needed to be on the driver's seat. No, they could be operating remotely on a very controlled environment, no, and they are connecting to their vehicles via 5G, no? And they could control it and very good real-time responsiveness. But there could still be a problem. I mean, you have a 5-tonner chunk of metal na, ravaging on the road, and suddenly was disconnected from the driver. No? So that car, at the very least, na, should notice that it was disconnected and start slowing down with all these sensors, of course, connected to it, and maybe park until the connectivity is restored. No? But it's going to be a problem too, no, for countries, developing countries. No? So if that truck would be carrying, no, precious cargo, I don't think they would use autonomous vehicle to carry precious cargo anytime soon. No? Let's say, maybe not good, but that could be a target for a theft, no? Or maybe they could some criminals might induce, no, disconnection, because they know that if this car gets this, or this truck gets disconnected, it would go to autosave mode where it would park itself on the nearby, and then they could do their theft there. No? So some things to consider. But maybe what I could say was I saw mining vehicles, no, because it's inherently dangerous, no, for mining vehicles operators, no, to be on site, no. So they were able to set them up near the site, and they're able to connect to their mining vehicles and operate them remotely to minimize any bodily harm in case anything goes wrong with that. So that would be a good use case. There's also accessible automation. No? So like telecoms, to a degree, that they're already implementing network automation on the edge, where maybe we could say, let's say, cell sites, no? Where let's say there's an outage of a cell site in the central business district, disconnecting, no, a lot of people. And if telcos, let's say, are using, no, this automation and failure recovery system, no, they could now instruct their edge devices on other towers that would say, na, okay, we have a blind spot here because of a failure of a telecom tower. Maybe someone's digging the road and suddenly cut, no, the fiber. No? So they could reconfigure their antennas, no, to be able to service that area on other towers within the circumference of that blind spot, no, and redirect their beam to the blind spot because, well, it's a central business district, so there's going to be a lot of users there. A bit degraded signal, no? It's not going to be as fast as you have a closed cell tower, no? But with network automation, they would still be connected again with some bandwidth reduction because you lost basically a cell tower. So all of this capacity would now have to be distributed across the other telecom towers. But would you rather have no connectivity or a degraded connectivity? So I would say I would want degraded connectivity rather than be disconnected at all. So all of this has been in operation with most telcos. No? So they are able to redirect the antenna with some motors, or even some of them would have been forming antennas, no? Where they would power up certain elements, no, that would make that signal be directed to a certain location, especially if no service there. And we've seen that it doesn't involve edge computing. Well, again, it involves edge computing, where you have access points that has been designed, no, with beam forming antenna, where you, let's say, you have a big field, no, and you connected to the access point. The access point would be able to detect where you are, your directionality, no. And on a big field where you maybe you only are 2 or 3 users, they could start directing, no, yung beamforming signal to the users. No? I mean, they can't direct anything more than maybe 5. No? But having a good range, no, for a 2 to 3 users on a huge field. No? Maybe it's a sensor network, maybe it's a user. That would also be good, no, cost-wise. No? Because now you don't have to deploy a lot of access points. No? The access point itself is able to handle longer range because it's able to compute, no, where you are and send the signal on your direction. So you could have more range now with lesser access points. We've seen this, no? We have streamlined analytics use case a while ago with the smart camera system use case. Again, it has to be designed in a way that you would be making use each and every step of the edge key components. No? Flexible pricing models, well, this mainly pertains to the cloud component of the edge computing because, well, you have to buy yung mga edge devices. No? So that's a given. But for cloud, no, at least the component for of cloud computing in edge computing, you basically remove the capex. No? So you would just be buying, no, services and pay as you use. No? So if the beauty of cloud computing with edge now is, let's say, again, going back, I like the smart camera use case. No? Sorry about that. But let's say you have a 10,000 camera system and at night, no, there's really not much activity in those cameras. But there would be a few. No? But you could just imagine that you would have more activity during the day than the night. No? So if you have your cloud computing component, no, here, no, set to auto scale, no, for cost efficiency, it would necessitate na you would have more compute power in the morning processing all these feeds and alerts, no? But at night where it's less, no, you could downsize it. No? You could give away these resources, and that would also means that you would pay less. No? But by the time the sun goes up, no, and people starts coming in, there's a lot more activity. No? You could now again resize your infrastructure and instantiate more compute nodes, no, to be able to handle that. And again, downsize it as needed. And if it's a holiday, no, that there's really not much activity, no, you would have, and weekends, no, you would have cost savings. No? And that would have effect sa flexible pricing models. Okay? And there's, well, with cloud, no, there's hassle-free regulatory compliance, since with my cloud talk last week. No? But also, the devices that you would be deploying, no, would also need to comply, no? Certain regulatory compliance, like especially for Wi-Fi, no? What's the amount of power? What's the frequency you're transmitting? So we would need to comply with on our end, no, NTC. But there's also environmental compliance. No? If we're gonna deploy this, you have battery. No? Would it affect the ground? Could it poison the ground, no? If those battery gets leaked, no? Or leaks, no? For some reason or the other. So that has to be also factored in. No? For cloud regulatory, no, it's more of their compliance with a lot of them is security and process optimizations. No? So, but most of them, most major cloud vendors, no, would be compliant to these regulatory requirements. Okay. So differences, no, with cloud computing. So this would be the last one. Again, how do we differentiate cloud versus edge? No, in simple terms, no, where the computation takes place, that's gonna determine if it's an edge computing or a cloud computing infrastructure. So again, edge computing would need to have processing capability on the devices itself or on the edge gateways near these devices. But cloud computing, everything is handled centrally in the cloud. But that doesn't mean the edge computing does not have cloud components. So but it's just that a lot of the grunt work is already performed on the edge devices and the edge server before being sent to the cloud. Okay. So first one, speed and agility. We got edge solutions that could have analytics capability and computational powers, close to the data as possible. For cloud computing, it's gonna be centralized. No? But for deployment, no, if you want to use this differences for deployment, you are more you could deploy faster in cloud computing because it's just via API or via menu. Now you want more computation, or you could even do it automatically via auto scaling. Now, for edge computing, though, you need to be purchasing these devices. You need to be deploying these devices. So, speed and agility goes to cloud computing as against to edge computing. But well, it has its own benefits. For productivity and performance, no, well, the faster you are able to give this information to the users with AI and machine learning and other analytical tools, no, in a few milliseconds you'll have your answers, no, as compared to cloud computing where you have to send everything there, you have to maintain these data centers, on-site data centers, and then they had to be processed and before being sent back to the users. No? So maybe I could make an example here where let's say Apple Watch, no? Apple Watch Ultra. The Apple Watch Ultra Siri on Apple Watch 1, you could record your command, no? Invoke Siri, record your state your command via voice. But what's happening there is it's just doing basic recording of your voice and then sending this command, no, to the cloud for processing. So there would be bandwidth implications. No? So and then sending the process data back to your device and then figuring out what you wanted to do. No? They upgraded this feature and it became as closer to edge computing model on Apple Ultra Watch 2, where the device itself could do the voice processing. And if it's a basic enough command, it could do it on the device itself. No? And basically, it did not have to send your voice data to the cloud for processing. So they could do it on-prem. So I could just see, no, or foresee that the future edge devices making it more accessible and very efficient, that they didn't have to send everything to the cloud. But of course, after the fact, no, those telemetry that for analytics purposes, na this user of Apple Watch Ultra 2, because they did not transmit the audio, no, they would have that log of activity, and they might report it to the cloud, no, for them to analyze, no, which features are actually being used by most people, no, and they would improve on that aspect of that product. And speaking of productivity and performance, no, so these are the amount of advanced neural engine performance. No, I got here an Apple product. So from iPhone 10, I think this was 7 years back. A11, we have 0.6 teraflops of compute advanced neural engine capability on the device itself. So this is what Apple was referring that they could do machine learning and AI to a degree, no, on the device itself. Compare that with iPhone 13, which is 4 generations away lang. It's 4 years away, no? It's 26 times than iPhone 10. No? Now you have 15.8 teraflops on iPhone 13. And we are now on iPhone 15, no? And in a few weeks, iPhone 16 is gonna get disclosed. No? So just imagine the amount of neural engine processing power those new devices would take. No? And I found this wiki, no, or if you could actually see, no, the amount of neural cores, no, for the M series um, chips of Apple. Apple M2 Ultra has 32 neural engine cores. No? And the Apple M4, no, which I think is in the newer iPads. No? It's weird that Apple released their newest chips on the iPad Pro, but it could use 38 trillion, no, peak operations per second on the device itself. So, well, there's not a lot of applications yet, no, that utilizes this, no? But it does its job. No? If you've seen applications that you could do handwriting, no, and it would just convert itself into text, no? That it's a handwriting recognition application. So I would assume that some of them would use this A&E course. No? So again, it's only going to increase. No? The amount of processing capacity on our device is just going to increase. No? So we'll have other use cases that we might not have thought of. No? That's going to be showing up, yeah, in the near future. So interesting times. Scalability, again, for edge computing, we're not that scalable because we need to buy equipments and items, no? And as a problem that or challenges that I have stated a while ago, sometimes you will not have the same devices. So you need to have it ensure interoperability, across various types and models of devices, and maybe again from different vendor. For cloud computing, scalability wouldn't be an issue. It's scalable, it's elastic, it's scalable up to your credit card, as the saying goes. You could have all the compute power you need, but you just need, of course, to pay for those. Reliability, again, this one would go to cloud, no? Because, well, for cloud, you don't have to maintain the power, the bandwidth, space. No? For edge computing, you deploy this equipment on harsh environmental conditions. No? Even your smart phone, no? It's on harsh environmental condition because you use it on a cold office room, use it outside when you're hiking, which is hot. You put it on your pants, no, which could be moist with your sweat. No, your smartwatch too would have similar issues. So, which are not a consideration for a data center hosting a cloud because they are on a very controlled environment. So even humidity is monitored, no, especially the temperature. And so that's the hardware reliability part. For connectivity, well, cloud computing would have high capacity fiber connectivity, no? Where in edge computing, you typically would have to rely on wireless, maybe even Bluetooth signaling. So, which does not have a huge range, no, and bandwidth. But as long as we get the data back from these edge devices, we can submit it to the cloud and edge gateways, we should be okay. Okay. And then lastly, security. No? So also discussed this a while ago where it's, I would say, a bit more easier to secure the cloud than edge computing, but do note, no, our discussion last week, there is a shared responsibility model to the cloud, so don't fall into the trap there that would say that it's in the cloud, so it is secure, we don't have to do anything. So that's not going to be the case. For edge computing, now, we have these devices that is outside our physical control. That could be stolen, that could be destroyed, that could have, no, unauthorized nodes, no, being programmed by nefarious threat actors to be able to connect to our infrastructure and cause issues. No? So yeah, so I'll just dump key learning points here.